In this video, we're going to talk about another bonding theory. It's called hybridization. And it's going to be more useful, far more useful to us than is valence bond theory. In hybridization, we're going to take some atomic orbitals and hybridize them, make these hybrid orbitals. And these hybrid orbitals are going to, of course, give us a correct electron domain geometry, a correct molecular geometry. One thing to keep in mind is the total number of orbitals at the start has to equal the total number of orbitals when we're finished. The fancy way of saying that is that the number of orbitals is conserved. So you've got the law of conservation of energy, law of conservation of matter, and now we're going to conserve orbitals. When we do this hybridization, it's always going to be the central atom that is hybridized. So that's something else to keep in mind. Only the orbitals on central atoms can undergo hybridization. So let's start out with a very simple molecule, beryllium hydride. Beryllium has a ground state electronic configuration of 1s2, 2s2. So it's only got 2 valence electrons. We have 2 hydrogens each with a valence electron. So we're only going to have 4 valence electrons in our Lewis structure. And this will be the correct Lewis structure for beryllium hydride. Yes, it's electron deficient, but that's all the electrons we have. And so just looking at this, we know it's going to be linear and 180 degrees for that bond angle. So we need to come up with these hybrid orbitals that will lend itself to having this bond angle. And so let's draw a box diagram for beryllium. And so we got this pair of electrons in the 2s orbital. So that's my beryllium in the ground state. So let's give it some energy. Let's promote an electron. So it costs us a little energy. We'll promote an electron from the 2s up to the 2p. We'll unpair it to spin in the same direction. So now we've got a beryllium in the excited state. So we're going to denote that with beryllium with an asterisk or a star. And what we're going to do is we're going to now take these 2 orbitals and we're going to hybridize them. And so we're going to have 2 hybrid orbitals. And we're going to have 2 unhybridized orbitals. So we start out with 4 orbitals with a beryllium. We're winding up with 4 orbitals. So we've conserved the number of orbitals. And these hybrid orbitals, they're just alike, and we're going to refer to them as being sp orbitals. sp orbitals. And so if we look at them, this beryllium, just like p orbitals having 2 lobes, these sp orbitals, they're going to be 2 of those. They're going to have 2 lobes. And so there's one of the lobes, and then let's see, how can I draw the other one? Maybe I'll draw it sort of like this. And there's the other lobe. And so each of these can overlap with a 1s orbital that's unhybridized from the hydrogen. So I'm going to simplify things a bit. I'm just going to draw a hybrid orbital like this. And you need to know that there's also the little bump, the other nodes, not nodes, but lobes that are there. those aren't electrons, but those are the lobes. And in the future, I'm just not even going to draw those at all to try to simplify matters. So there's my beryllium. And there's an sp orbital. There's an sp orbital. And we're only showing the big lobe out of each of those. And there's my 1s orbital from my hydrogen. I got some overlap, and those give me my bonds. And so that's a hybridization model for the two bonds that are 180 degrees from one another, and that matches what we would see in nature. These bonds are also called sigma bonds. This little figure is a sigma, a lowercase Greek sigma, lowercase Greek s. And a sigma bond means that the overlap is along the internuclear axis, that the bond lies along the internuclear axis. It's just a fancy way of saying directly between the two nuclei that are involved. Let's now look at boron trihydride. Here's a Lewis structure, and I've drawn it to try to give you a hint at the bond angles. There are 3 electron domains, so it's 120 degrees or trigonal planar. And so for all these hybridization theory, we're sort of working from the actual molecule itself back to what the hybridization would be. Boron, 1s2, 2s2, 2p1. All we care about are those valence electrons. So there's my 2s and my trio of 2p orbitals. So there are my 3 electrons. That's boron in the ground state. I'm going to give it some energy. I'm going to promote an electron. So there's my 2s, and those are my 2p. So you got 1, 2, 3 electrons. So I'm promoted. And now I'm going to undergo hybridization. And that those 3 orbitals that have an electron in each of them will become my 3 hybrid orbitals. And I'll have an empty or unhybridized 2p orbital. So these hybrid orbitals, we'll call those sp2. sp2. That's not sp squared. It's not sp squared. What this notation is showing us is the number of each type of atomic orbital that we use to hybridize. So in essence, it's sort of like S1P2, but there's only ever a single S, so we simplify that and just call it sp2. Not sp squared, but sp2. And so now we've got a trio of hybrid orbitals. Once again, they have these double lobes. And actually, I can sort of draw those in here. Doesn't complicate things too much. And so that's my sp2, sp2, and sp2. There's my hydrogen with its unhybridized 1s orbital. Got me some overlap. And so now I've got 3 sigma bonds. 3 sigma bonds, because the bonds lie directly along the internuclear axis, hence we call sigma. Since we come up with these names, having to note that, you might think ahead that there's going to be another type of bond where the overlap's not directly along the internuclear axis. We'll call those pi bonds, but that'll be a couple videos down the way here when we talk about multiple bonds. And so we've got a trigonal planar geometry now. in our boron trihydride, or boron hydride. Now let's go back and do our methane that we talked about in a previous video. Remember, it's the central atom that hybridizes, so we care about that carbon. 1s2, 2s2, 2p2, those 4 valence electrons. So there's my 2s. There's my trio of 2p orbitals. I've got a paired up electrons in the 2s, and I've got an electron in each of a pair of 2p's. I want to promote. So there's my carbon, the ground state. Now I'm going to make carbon an excited state. So there's my 2s, my 2p's. Promote an electron. So now I got 4 orbitals, each with an electron in them, that cost me energy. But now I can hybridize and gain that energy back by having a quartet of hybrid orbitals. And how did we make that? From an s and from an s and from 3 p orbitals. So this is called sp3. This is actually a quartet of sp3 orbitals that all have a single electron in them. And so now we have 4 equivalent orbitals that are all sp3. They're hybrid orbitals. They can overlap with the 1s orbitals. They are unhybridized from the hydrogen. And so I've got 4 bonds that are just like. They're 109.5 degrees. They are tetrahedral. And so that's how we can use hybridization to talk about 2, 3, and 4 electron domains. In another video, we'll talk about 5 and 6 electron domains and how we can go about doing that hybridization.